Good morning, folks. Today we're taking a look at kinematics in 2 dimensions. So technically we've already looked at kinematics in 2 dimensions, but we're going to focus a little bit more on objects that are turning in direction. So projectile motion, strictly speaking, is kinematics in 2 dimensions. Well, technically it could be kinematics in 3 dimensions, but let's not get ahead of ourselves. Okay, so in previous units in kinematics, when we did it in grade 11, we were just focusing on 1 dimension. And what that meant is that, say, for example, we had d is equal to v1t plus 1/2 at squared. This ran under the assumption that these vectors were all collinear, i.e. the velocity, the displacement, the acceleration would either be on the x-axis or on the y-axis. So we would either have forwards and backwards, left, right, up, down, north, south, east, west, that sort of situation. But in these examples, we're actually going to have the objects experience turning. And that, of course, adds a certain level of complexity. So before we can do that, let's just sort of remind ourselves of some of the key concepts. So the idea of average speed, that's defined as the total distance over the total time. Now, when we compare that to the instantaneous speed, it's really the same formula. The only difference, it happens over a much shorter time period, i.e. t is approaching 0. And when you look at the speedometer on a car, it's quasi showing you instantaneous velocity. It's not exactly instantaneous. And the reason being is if they were looking at the instantaneous, the speedometer values would be jumping all over the place and being quite distracting. So, well, they're designed to take those values over a limited time period, so it sort of smooths things out. And that's basically what averaging does. It kind of smooths the peaks and valleys and whatnot. But strictly speaking, the instantaneous is over very, very short time periods. In calculus, we refer to this as a differential. And those of you who are in the process of taking calculus, you may be starting to talk about things like instantaneous rate of change, the derivative. These are all sort of related. Now, the same big idea applies for average velocity and instantaneous velocity. So the average velocity is the total displacement divided by the total time. Now, just to clarify, when we talk about total displacement slash change in position, there are two ways of measuring the same thing. It just all depends on how the information was given to you. So for example, let's say you walked 3 meters east, then 4 meters north. Your displacement vector would be the hypotenuse. So let's call that vector A, let's call that vector B. So in this case, you're actually adding these two vectors. So to get the total displacement, it's vector A plus vector B. And that's because in this particular case, we gave you two different paths that were taken. So path 1 was 3 meters to the east. Path 2 was 4 meters north. We would use vector addition, and of course that in this case would be Pythagorean theorem, and we would get a magnitude of 5, and then of course you find your angle. So that is one way you can find displacement. But sometimes we're given position vectors. Allow me to elaborate, I should say. So here we have our frame of reference. And I don't know, let's say for the sake of argument, this is the flagpole at the front of the school. And instead of actually giving the two legs of the pathway, let's say your initial position, and let's call that your D1. Let's say that is 3 meters to the east. Then let's say, for the sake of argument, you walked to a position that was 4 meters to the north. Didn't plan my space very well. 4 meters to the north. The struggle is real, people. Okay. So now what this has given us is your initial position here and your final position there. What it didn't give you is the path taken, just the initial and the final position. And I should put a subscript 2 there if we'd like to do that accurately. So your displacement would be represented by this vector here. That would be your displacement. So in this case, to figure out the displacement, it's your change in position, which is the implied delta, D2 minus D1, position 2 minus position 1. And that's where you get your delta in terms of the displacement. That's why it's an implied delta there. And the reason why that's an important distinction, it all depends on how the data is originally presented to you. So technically, you could have walked the following pathway because it doesn't describe the route that you took. So you could have done this, walking around, tra-la-la-la-la, and then eventually get to this point there. So in this method, it doesn't tell you anything about the legs of the journey that you took. It simply gave you the final and the initial position. So that's why when calculating the displacement, context is everything. All right, it's getting into a bit more minutia than I intended, but these are things that need to get clarified anyway. Now, you'll see that under instantaneous speed and instantaneous velocity, I refer to the slope of the tangent. And that's basically on a curve when you're graphing something. Now, you know from grade 11 that instantaneous velocity and instantaneous speed are not my apologies. Average velocity, I should say, and average speed are not necessarily going to be the same value, especially if you are not walking in a straight line. If you're walking in a perfectly straight line, your distance and your displacement are equivalent. So for example, let's go over here, we have a little bit more real estate. So let's say we walk directly from point A to point B. So this vector here represents your displacement. But if you're walking in a straight line, represented here in the green, the magnitude of the displacement and the distance, well, they're going to be the exact same. However, let's say we started at this position here and ended at that position there. And in that case, let's say the actual journey was something like this, kind of a curvy path. Let's say we're walking along a river or something like that. Our distance is the full length of this pathway, but the displacement is the straight line connecting the initial and the final position. It's a vector, has a magnitude and a direction. And here you can see that the magnitude of the displacement is less than the distance. And that would mean that the magnitude of the average velocity would be less than the speed. And of course, to make things confusing, we use the same letter for speed and velocity. So you have to be careful because V without a harpoon is implied to mean speed, unless the context of the question makes it very obvious that you're talking about velocity. So often I'll be using this more complex notation if there's ever a chance that we can confuse it with speed. Now, back in grade 11, we didn't really have those problems to deal with because we were generally going in a straight line. Okay, so let's take a look at this graph here. So here I have a graph of some accelerated motion and I have position versus time. So as you can see here, we have a positive facing parabola. So if we take a look at a couple of positions here, so we're at a position of +4, and after 1 second, looks like we're at a position of 2.25. After 2 seconds, we're at a position of 1. So this object is moving backwards. And then at the 4-second mark, we're at the 0 position. And then it starts to move forward. You can see at the 6-second mark, we're at position +1 again. At the 7-second mark, we're at position 2.25. And at the 8-second mark, we're back at a positive position of 4. Now we consider this to be positive acceleration. Let's color code it. I usually use purple to represent my accelerations here. Now, how do we get positive acceleration? Well, what we have to do is we have to look at the instantaneous velocities at each of these points. Now, that's where we get what I refer to as the slope of the tangent. So I'm going to draw a tangent line, and all a tangent line is what I referred to last year as a mini slope, i.e., looking for the slope trend at that point. So let's take a look at the next section here. So what we're trying to do is we're trying to match the slope at this point right here. So this is our mini slope that I'm referring to. And as you can see, when I zoom in, I'm looking at a very small delta D and a delta T. So that's where we're getting our instantaneous. Now, the trick to drawing these things on real life graphs is you try to get it so that the gap on either side is even, as close as you can. Obviously, this is an approximation method. We have a more rigorous mathematical system of doing this. So what this tells us is the slope of this tangent line is the slope of that point. That's our instantaneous rate of change, i.e. our instantaneous velocities / instantaneous speeds. So if we look at this trend in the slope, so here we have negative velocity, but now the slope is starting to level out. It's becoming less steep. So this is becoming less negative velocity. As we go along, increasingly less negative. And then when we get to the 4-second mark, you can see that the slope is 0. So here we have a velocity of equals 0. And then on the other side, our velocities are changing to positives. So the slope of the tangent, let's get that a little bit more tangenty. So that's positive velocity, and it's increasingly becoming more positive. So as you can see, the reason why it's a positive acceleration is because the positive acceleration means that our velocities / speeds are trending towards the positive velocities. So we go from negative to less negative to zero to positive to more positive. That is a positive change. It's like the temperature outside going from -5 to 0 to +5 to +10. It's a warming trend. Even if it went from -15 to -7, it's still a warming trend because it's moving towards the positives. So these slopes at these points, these are referred to as your instantaneous speeds / instantaneous velocities. Now, the very, very important idea here is that when we look at the instantaneous, the numbers become the same. And here's the reason why. If you zoom in really close to a curve, the curve approximates a straight line. This is a very confusing concept for flat earthers. They wrongly assume that the earth is flat because they struggle to detect a visible curving of the surface. And that's because when you're really looking at a microscopic scale, it's really hard to see that change. Even if you have a pool of water, like a swimming pool in your backyard, the water level is technically not flat. It's curved slightly. It's just the degree to which it's curved is so minuscule compared to our visual acuity that we simply just do not notice it. However, when you look at the macroscopic scale, well, that's when things get a little different. So let's take a look over the following time interval. Let's take a look, and I'll use a different color here. I'll use fuchsia. So let's take a look at the 2-second mark, and then let's take a look at the 6-second mark. So if you were to take a snapshot at the object at 2-second mark and the object at the 6-second mark, they are in the exact same position. Hence, the slope of this line is 0. So the average velocity is going to be 0 meters per second because over a duration of 1, 2, 3, 4 seconds, there has been no change in position. However, in terms of average speed, well, that's going to be a little bit different because the distance in the first 2 seconds, we walked a distance of 1 meter back. So that's -1, but a magnitude of it, a magnitude of -1, because distance does not have a direction. And then in the next 2 seconds, we walked an additional 1 meter, but this time in the forward direction. So plus +1. So over that same time interval, the distance was equal to 2 meters. So the average speed is going to be the distance over the time, which is equal to ½ meter per second. And that's the big difference. So the average velocity and average speeds don't necessarily equal each other, especially when we're not consistently moving in a straight line. Here, we had a moving forward and back. It gets even weirder when we start changing directions and whatnot. So again, the concept, and we're going to focus on average velocity, it's really just your change in position over your change in time. So for something like this, let's take that right there. The slope of this line, more or less a secant, I guess, this represents your average velocity. Pretty terrible average. Let's try that again. Oh dear. The average. And that's going to be the slope of this line right here. However, your instantaneouses, they're going to be radically different. So the instantaneous velocity at the beginning is going to be 0. And over here looks to be around, I don't know, maybe a slope of 1, just kind of eyeballing it here really, and so on and so forth. So these are your instantaneous velocities. Those are the slopes of the tangents at any given point, where the average is your total displacement over the total time. So what happens when we start to turn? Okay, so let's take a look at this example. Michael walks north at a constant rate. In 10 seconds, he walks 10 meters. Okay, so now in this first leg, let's just call this A, we'll call the second leg B. Calculating the average speed, pretty simple because it's 10 meters. That's the distance covered divided by 10 seconds. So the average speed is 1 meter per second. Now, the interesting thing, since Buddy's going at a constant rate, the instantaneous speed is going to be the same, 1 meter per second, because there's no acceleration during that. Then he turns west, but then he west. Okay, so our Buddy is westing apparently, and walks an additional 15 meters at a constant rate for 10 seconds. So in this second leg, the average velocity, well, that's going to be your change in position over your change in time. Oops, I sort of jumped the gun here a little bit. Let's go back here. We're not talking about the section B yet. Yikes. Got a little ahead of myself. Sorry about that. So we're still talking about section A there. Let's get back to it. So the instantaneous speed, 7 seconds, 1 meter per second. Sorry, now we got to talk about the average velocity. Well, no surprise because we're going in a straight line. The average velocity is the change in position over the change in time. So that's 1 meter per second north. Same as the average speed in this case, because again, in the first section, we were traveling at a constant rate in a straight line. So average velocity, average speed, same deal. Instantaneous velocity is going to be the same as the instantaneous speed, just it has a direction. Okay, so now let's talk about the average speed over the 20 seconds. Okay, well, now that's a little bit different. So now when we talk about the average speed, because in the second leg, he travels 15 meters towards the west. So when we're talking about distance, the distance is just the magnitude of A plus the magnitude of B. So I guess I kind of did this in a weird sort of way here, but you basically get the idea. So that's a change of 25 over 20 for an average velocity of 1.25 meters per second. Now let's focus on the second leg. Okay, so then in the second leg, the average speed over the last 10 seconds. So Buddy traveled 15 meters in 10 seconds. So that's an average speed of 1.5 meters per second. So at instantaneous speed at 12 seconds, well, it's going to be the same thing because we're at constant rate in section B. That's 1.5 meters per second. Average velocity, same deal, but this time it's got direction. And the instantaneous velocity, same deal because it's a constant rate and in the same direction. But all that changes when we talk about average velocity, because now the average velocity is either your change in position or your change in time or your total displacement over the total time. Well, in this particular case, and just to clarify it, and this is the old days when I used slightly different notation. Here, the displacement total, and that's how I'd normally write it, is equal to our first leg plus our second leg, because we weren't given the initial and final positions. We were given the first path and the second path. So when you do vector addition, we get the displacement as a sum of these two vectors. So how would that be different? How could I do that actually as a delta? Well, if we were to do that as a delta, we'd have to do something like this. I'd have to use, say, this position as my reference position and have my first position, my D1, as being 10 meters south, i.e. we started here and I was initially 10 meters south of this position. And then I moved to a position that was 15 meters to the west. So that nuance is very important, that you understand the difference between the two. So I didn't give you positions, because if we did it this way, then the displacement is the change in positions, which is your vector D2 minus D1. It will give us the exact same result, but if the data is presented in a different way, you have to adapt to how it's communicated. So you have to understand recognize the difference between whether you're given position or if you're given each individual leg of the trip. So in this case, we had each individual leg of the trip. So we do vector addition right there. Okay, as opposed to vector subtraction. Make that a little bit cleaner. Okay, so anyway, that was a lot of qualifying just to get down to the nitty-gritty. If we're trying to find the average velocity over the 20 seconds, we have to find the magnitude of the displacement. And of course, that's going to be based on the shape that we have here, which is a right angle triangle. And since we have a right angle triangle, it's Pythagorean theorem, and we have a magnitude of 18 to a terrible approximation because I just rounded it off to 2 sig figs. So obviously there is significantly more calculator vomit. So actually that's not even worthy of a amber check mark. That's worthy of a very, 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 very dirty check mark. That's a pretty low quality answer there, but you get the idea. Now, of course, we also have to find the angle. And of course, based on this, since we're going to be using SOHCAHTOA, this is the opposite side, this is the adjacent. So we're going to be using tangent, and we get an angle of 56 degrees to 2 sig figs. Okay. So the next step, of course, is to find the average velocity. We take the magnitude of the displacement divided by the time. So that's our 18 divided by 20, our 0.9. Yikes. Not really following the rules of sig figs here very much, but you get the idea. So of course, we get an average velocity of 0.9 meters per second, and the angle of north, 56 degrees west, because our theta is here and our first vector is north, then our second vector is west. Easy peasy, lemon squeezy. Now we'll contrast that with our average speed, which was 1.25 meters per second, which makes sense because the distance covered in the same amount of time had a greater magnitude. Okay, so let's just take a look at the first couple of sample problems here. So example 1, a bird dives at a velocity of 15 meters per second down, and at the last minute levels out to 25 meters per second towards the left in a span of 15 seconds. Okay, so taking a look at the solution here. So we're trying to find the two things, the bird's change in speed and linear acceleration, and the change in velocity and the vector acceleration. Okay, so this V1 represents the initial velocity. This V2 represents the final velocity, and the change in time is that 15 seconds. So the first thing, let's take a look at the change in speed. So the change in speed is just your final speed minus your initial speed. So we're just looking at the instantaneous, because the instantaneous velocity and instantaneous speed are always the same value. And that's always true. The instantaneous, that is. Not the averages, but the instantaneous. Okay, so we get a change of speed of 10 meters per second. Now, to find the velocity, the average acceleration, that's going to be your change in speed over your change in time. So 25 minus 15 over 15, that's 10 over 15 or 0.6667 meters per second squared. So calculating the linear acceleration is very, very, very trivial. However, things get interesting when we have to do the vector stuff. So when we do the change in velocity, delta V is equal to V2 minus V1. Now, when you do vector subtraction, there's two ways that we can do that. So we can do the subtraction directly, and to do that, we have to put the vectors tail to tail. Just going to thicken these up a little bit so it's a little easier to see. Okay, so now you might be more comfortable with the idea of vector addition. So alternatively, we could look at it like this. Delta V is equal to V2 plus negative V1. Okay, so now what does that look like? I just made a copy of our V2, and here's a copy of the V1. All right, I'm going to change the color to this. So that's our V2. Now, I need to make this a negative V1. Well, to make it negative, it means it just flips direction. So the negative V1 is just in the opposite direction of V1. So now when we add them together, V2 plus negative V1, and the resultant is going to be this vector here, which lo and behold is the exact same vector that we get over there. So although adding vectors is maybe a little bit more intuitive, it's a kind of a waste of time if we're going to constantly do this. So what we do instead is we always do tail to tail. The question is, when you do tail to tail, how do you know where to put the head of the resultant? So the easiest way to remember, it always starts at your initial and goes to your final. So your initial was your V1. So we start at the head of V1, and your final is your V2. So it always points from the end of the initial to the end of the final. And if that's confusing you a little bit, let's go back to the example I gave with respect to the flagpole in the front of the school. This represents your initial position. This represents your final position. So this is your D1, this is your D2, and your displacement would be defined by the change, D2 minus D1, because we started here and we ended up here. So initial, start, final, finish. And that's the easiest way to remember it. Okay, so now that we've established that, we have to find the magnitude of the change of velocity. So again, using Pythagorean theorem, and this reduces down to 5 root 34. That's a much better quality answer. That deserves an amber check mark. For this one deserves a dirtier check mark because of the rounding. And our change in velocity, therefore, is going to be, the magnitude, I should say, is going to be 29.15 meters per second. Of course, we still have to find the angle, and we use tangent for that, which is your opposite over your adjacent, taking the arctan of the magnitude of V2 over magnitude of V1. And you can see here by context, we know that we're talking about velocity. So then you can just drop it and use this notation here safely. We get an approximate angle of 59.04 degrees. So therefore, a change in velocity is 29.15 meters per second. And that's going to be up 59.01 degrees to the left. Now, what might be really confusing is that the bird, presumably it did something like this. Right? So it was diving down and then swoosh like that. So the question is, how the heck is the change in velocity have anything to do with an upward component? I mean, the left component makes sense, but the up component, that's very strange, isn't it? Okay, so you have to think about it. The change in velocity is related to our acceleration, and acceleration is related to the force, the net force specifically. So calculating the average acceleration is going to be your change in velocity or change in time. The heavy lifting was trying to find the change of velocity. So to find that magnitude is just this value, 29.15 divided by 15. So now what we've got is we've got an average acceleration of 1.943 meters per second squared, up 59.04 degrees to the left. Okay, so what that means, folks, is that the net force acting on this object has an up component and a left component, which if you think about it, makes sense because the bird was initially moving in the downward direction and then is no longer moving downward, which means that there must have been a force stopping its downward descent. That's probably redundant saying downward descent. But it's downward motion. So it went from having a y component of velocity of a negative y component to 0. Well, for that to occur, that must meant that there must have been a force acting in the y direction like this. So that's a force in the y component. And then initially it did not have any motion along the x-axis. It was going downward, but then it was pushed towards the left. So what that must have meant is that it also experienced a force towards the left, and we end up getting a net force, which is the combination of the two. And that would be our F net. So that explains why the change in velocity and the acceleration is in that direction, because it's related to the forces acting on the object. Okay, so next I want you folks to take a look at example number 2 and try example number 3. Now, of course, I do have the pre-made solutions, and those can be found over here and here. And then we will take those up later.